The CH-53K King Stallion is the U.S. Marine Corps' newest heavy-lift helicopter, designed to carry more weight, farther, and in harsher conditions than any of its predecessors. Developed by Sikorsky, a Lockheed Martin company, the CH-53K combines advanced composites, high-power turboshaft engines, and digital avionics into a platform capable of lifting up to 36,000 pounds externally in demanding high-hot environments. Over the next 16 minutes, this film walks through the entire production and test process, from raw materials arriving at the factory, through structural assembly and system integration, to ground runs, flight test and delivery, showing how thousands of individual parts are transformed into a frontline marine heavy-lift aircraft. The story opens on the flight line outside the Sikorsky facility, where completed CH-53K King Stallions stand in a row on the concrete apron, their low-visibility gray paint blending with the overcast sky. Each helicopter stretches roughly 30.2 meters from nose to tail and stands about 8.6 meters high, dwarfing the ground crews working around them. These dimensions are not just impressive numbers, they represent the volume needed to move armored vehicles, pallets of ammunition, or dozens of Marines from ship to shore and deep inland. Technicians in dark blue coveralls and white hard hats move between aircraft, connecting ground power, inspecting rotor heads, and preparing airframes for test flights or delivery to the U.S. Marine Corps. From the ramp, the camera transitions inside the main final assembly hall, a cathedral-like space with yellow overhead cranes spanning the production bays. Several CH-53K fuselages occupy parallel assembly positions, each at a different stage of the build sequence, from bare structural shells to nearly complete airframes. A digital board above the line displays key metrics: length 30.2 meters, cabin width 2.6 meters, maximum gross weight 88,000 pounds, figures that drive every structural requirement, lifting fixture design, and handling limit inside the plant. Multi-level platforms give technicians access to the nose, center fuselage, tail boom, and roof, turning the huge airframes into manageable workscapes. To understand how these helicopters come together, the film rewinds to the beginning: materials preparation. In the materials storage area, tall racks hold rolls of carbon fiber and composite fabrics that will become critical components such as main rotor blades and tail rotor flex beams. Nearby, titanium billets and aluminum plates are stacked and bar-coded. Titanium will be machined into high-strength fittings, beams, and gearbox mounts, while aluminum will be formed into frames, ribs, and fuselage skins. An engineer scans each batch with a handheld barcode reader, linking every piece of material to a digital traceability record so that its origin, lot, and certification are known for the life of the aircraft. In the machining area, a 5-axis CNC machine goes to work on a block of titanium, cutting away metal with remarkable precision. The part emerging from the billet may be a structural beam supporting the main gearbox, or a critical joint where engine loads enter the fuselage. As metal chips and coolant stream away, a monitor displays tool paths and tolerances measured in thousandths of an inch, ensuring each component can withstand the torque and vibration produced by the CH-53K's 3 engines. Next door, huge presses form heated aluminum sheets over contoured dies, producing curved frames and skins that match the helicopter's aerodynamic and structural requirements. These skins will eventually be primed, sealed, and painted in the familiar Marine Corps gray. But at this stage, they are bare, waiting for further processing. Industrial robots play a central role in constructing the fuselage shell. One work cell shows a robot drilling and riveting patterns of fastener holes along internal panels. The spacing, angles, and depths are all driven by 3D digital models and structural load analyses. This combination of high-precision drilling and automated riveting creates joints that are strong, consistent, and lighter than hand-built equivalents. In another area, composite panels destined for structural floors, roofs, and bulkheads undergo ultrasonic inspection. Technicians slide probes across the surfaces, watching echo patterns on screens to detect voids, delaminations, or inclusions long before the parts are buried inside the aircraft. The camera then moves into the fuselage section assembly zone, where the helicopter is broken into major modules: nose section, center fuselage, and tail boom. Each module sits on an alignment jig that supports the structure while technicians install frames, stringers, and skins. On a nearby wall, a large technical poster shows the CH-53K in side view, labeled with overall length 30.2 meters, height 8.6 meters, 7 composite main rotor blades, a 4-blade tail rotor, and a cargo cabin wide enough to carry tactical vehicles or up to 55 troops with sidewall seats. Engineers frequently reference this visualization to confirm that the build is tracking the design at full scale. A close-up reveals a metal data plate on a workbench being engraved with the helicopter's designation, CH-53K, King Stallion, along with callouts for 3 T408 GE 400 engines and the 7-blade composite main rotor system. This data plate will be mounted on the aircraft and will follow it through every inspection and maintenance event across decades of service. Back on the center fuselage jig, technicians install longitudinal stringers and frames, forming the spine that transfers flight loads from the rotor system, tail, and landing gear into the airframe. Welding robots strengthen key joints in high-stress zones, while long external skins, currently in greenish primer, are riveted to the structure by automated machines that sweep along the fuselage length. Attention shifts to the sponson assembly area, where large composite sponsons are built up to house fuel tanks and portions of the landing gear mechanism. A cutaway display and 3D animation demonstrate how the sponsons integrate structural shells, fuel volume, and attachment points to the main fuselage, highlighting why composite construction and careful geometry are essential for weight and durability. Once complete, each sponson's outer surface is primed and ready to be painted gray to match the rest of the aircraft. Overhead cranes then lift the center fuselage module onto a precision alignment jig. Technicians align indexes and clamp the module in place. In subsequent shots, robotic arms and workers attach the sponsons to the fuselage, torquing bolts according to detailed procedures. The tail boom, a long, slender section that will carry the tail rotor and associated gearbox, is then brought to the fuselage. Technicians use red alignment lasers running along the join line to make sure pitch, yaw, and roll attitudes fall within tight tolerances, since even small misalignments can affect handling and fatigue life. Once the nose, center fuselage, tail boom, and both sponsons are bolted and sealed together, the airframe reaches its full length. With a uniform primer coat from nose to tail, ready for gray paint in later stages. With the core structure complete, the film moves to the composite rotor blade shop. Here, automated fiber placement machines lay carbon fiber tapes into large molds that give the main rotor blades their distinctive twist, thickness distribution, and aerodynamic profile. After these layups are completed, they go into massive autoclaves where heat and pressure cure the resin, turning layered fiber into a single cohesive composite structure. Once cured, each blade undergoes CNC trimming of its leading and trailing edges, drilling of root attachment holes, and surface finishing. The blades then go on to balancing machines, where small weights near the tips are adjusted to bring vibrations into acceptable bands. A separate area produces flex beam components for the tail rotor, using similar composite processes tailored to the tail's loading environment. Meanwhile, the heart of the propulsion system is being assembled in the engine shop. The CH-53K's 3 General Electric T408 GE 400 turboshaft engines represent a significant leap beyond the engines used in the legacy CH-53E, offering roughly 7,500 shaft horsepower each. The film shows turbine discs being populated with blades, technicians checking clearances, and completed engines mounted on test stands where fuel and instrumentation lines are attached. During engine runs, the control room monitors shaft horsepower, exhaust gas temperature, and vibration levels to ensure each engine meets specification before installation. In parallel, the split-torque main gearbox is assembled in a specialized cell. Large gears and shafts are lowered into the housing, forming a layout that divides torque into multiple paths, so that no single gear or shaft must carry the full engine load. This approach allows the gearbox to handle the combined power of 3 T408 engines without becoming unmanageably heavy. Bench testing circulates lubricant through the gearbox while an electric motor spins the system. Technicians watch temperature and vibration readouts through inspection windows and on digital gauges. When the gearbox passes its tests, it is moved to final assembly on a wheeled trolley. On the fuselage, the tail rotor drive system begins to take shape. Mechanics install a long-tailed drive shaft along the top of the aircraft, mounted on multiple support bearings along the fuselage length. A laser alignment device checks that each coupling and support falls along a consistent center line, reducing stress, wear, and noise in the tail rotor drivetrain. In another bay, engines that have already passed acceptance tests are staged on racks, each tagged with serial numbers and CH-53K markings, and matched to a digital build record that ensures traceability for the life of the aircraft. Final assembly brings all of these systems together. A yellow overhead crane lifts the fully skinned nose section and slowly lowers it into position against the center fuselage. Engineers measure gaps with feeler gauges, inspect edge alignment, and only then authorize sealing and final bolting. The tail boom module is attached in similar fashion, using lasers and measuring tools to confirm that the combined fuselage maintains the correct geometry over its 30+ meter length. Sponsons previously built and tested are lifted and secured to either side, reinforcing the helicopter's stance for landing gear installation. Landing gear work follows a carefully orchestrated sequence. Main landing gear struts are installed into reinforced volumes within the sponsons, where they will carry the weight of the helicopter during ground operations and landings. Technicians torque large pivot pins to specified values and verify that retraction and extension will occur within mechanical limits. At the front of the aircraft, a steerable nose gear is fitted into its bay, and hydraulic lines and steering sensors are connected. Inside the cargo compartment, the metal cargo floor is laid down and bolted, integrating tie-down rails to secure internal payloads ranging from vehicles to pallets. The large rear ramp, which will allow loading and unloading of heavy cargo, is installed with dual hydraulic actuators, and its movement is tested repeatedly while connected to laptops that plot ramp angle against time and hydraulic pressure. Attention then shifts to enabling the aircraft's mission from the inside out. In the cargo bay, folding troop seats are mounted along the side walls, and placards are applied showing maximum internal payload configurations and troop layouts for the 2.6-meter wide cabin. Technicians in the cockpit install glass cockpit components, multifunction displays, control display units, and central panels, reflecting the CH-53K's transition to a fully digital flight deck. This modern avionics suite, integrated with a full-authority fly-by-wire flight control system, allows precise handling while reducing pilot workload and improving safety margins compared to legacy mechanical controls. Behind the scenes, avionics technicians route bundles of electrical and data cables along internal frames, secure them with clamps, and connect them to avionics racks that house mission computers, communication radios, and networking equipment. These systems are designed to plug the CH-53K into the wider Marine Air-Ground Task Force and Joint Digital Environment, supporting shared situational awareness and coordinated operations. Sensors for pressure, temperature, vibration, and structural loads are distributed throughout the airframe, feeding data into health and usage monitoring systems that help maintenance teams identify issues before they become failures. On the helicopter's roof, major drivetrain installation begins. The main gearbox, already tested in its own cell, is lowered into its pylon mounts atop the fuselage, where it is bolted and torqued according to stringent procedures. One by one, the three T408 GE 400 engines are lifted into their rooftop positions and attached to their mounting points around the gearbox. Fuel, oil, and sensor lines are connected and routed along structural beams, secured with clamps to prevent chafing and vibration-induced fatigue. A laser-based alignment check confirms that engine-to-gearbox couplings sit within allowable misalignment to ensure smooth power transfer. Next, the rotor system comes together. The assembled main rotor hub and flex beam package is craned onto the main rotor mast and secured with hardware designed to carry the enormous lift and bending loads of a heavy-lift helicopter. Technicians then lift each composite main rotor blade into place and attach it to the hub's root fittings, tightening bolts with calibrated torque wrenches and verifying match marks that indicate correct orientation. At the tail, the rotor hub and 4 composite tail rotor blades are installed on the tail rotor gearbox, completing the primary lifting and directional control surfaces. Before any paint is applied, the aircraft undergoes a series of functional and integration tests while still in primer. Inside the cockpit, test pilots and flight engineers power up systems and run built-in test sequences on the displays, checking that engines, hydraulics, electrical power, and flight control computers report OK status. Moving the cyclic, collective, and pedals causes the swash plate and pitch links on the roof to move in precise, commanded patterns, demonstrating that the fly-by-wire system is properly tuned and communicating. Under the fuselage, technicians connect hydraulic service equipment, monitor for leaks, and cycle landing gear and ramp actuators, while watching pressure and flow data on laptops. Once structural integrity and system behavior meet specifications, the helicopter is towed into a large paint booth. Corrosion-resistant primer is applied first, crucial for naval and expeditionary operations, where salt, moisture, and temperature extremes are common. After the primer cures, the low-visibility gray topcoat, characteristic of U.S. Marine Corps aviation units, is sprayed onto the fuselage, rotor components, and sponsons. Painters then mask and apply national insignia, Marines markings, aircraft serials, and warning stencils in subdued tones to minimize detectability while preserving identification. Under bright inspection lights, quality teams check the finish for coverage, texture, and defects. With painting complete, the aircraft is rolled out to an outdoor ground test pad for final systems and propulsion checks. Technicians connect instrumentation to dedicated access points along the fuselage and sponsons, enabling real-time recording of structural and system parameters during engine runs and rotor operations. Ground tests begin with individual engine starts, rotor engagement, and idle checks, gradually progressing to higher power settings. Dust and debris swirl under the 7-blade main rotor as the helicopter lifts weight off the landing gear during initial hover checks. To prove its heavy lift capability, the CH-53K is subjected to external lured trials. In one test sequence, the helicopter hovers, with a large instrumented test weight block suspended from its belly cargo hook, representing an external load up to 27,000 pounds in challenging conditions. Engineers in a nearby truck monitor load cell data and vibration signatures, confirming that the hook, supporting beams, and airframe behave as designed under load. After successful ground and hover testing, the aircraft moves to runway trials and initial flight test. Taxi tests verify nose-wheel steering, braking, and overall handling at low speeds, ensuring there are no surprises once the helicopter leaves the ground. When cleared, the CH-53K lifts vertically from the runway, transitioning into forward flight as telemetry streams to a flight test control room filled with engineers monitoring speed, altitude, engine margins, structural strains, and system behavior. Over a series of flights, the test team expands the envelope, validating a cruise speed around 170 knots, operation up to altitudes around 16,000 feet, and performance margins in high-temperature, high-altitude scenarios that far exceed those of earlier CH-53 platforms. As the film approaches its conclusion, A newly tested CH-53K King Stallion returns to land near the factory and taxis to the ramp, where it parks alongside an older CH-53E Super Stallion. A tracking camera slide reveals key differences. The CH-53K's more streamlined engine nacelles, its 7-blade composite main rotor, and a heavier gross weight and external lift capacity that give it roughly 3 times the external lift of its predecessor in some conditions. Rows of operational CH-53K helicopters in low-visibility gray stretch into the distance, representing a new heavy-lift backbone for the Marine Corps, built around powerful engines, advanced rotor technology, and digital avionics. This aircraft is designed to sustain sea-based and expeditionary operations in contested environments for decades to come.